EE World. We are at the 6G Symposium in Washington, D.C. And we have Hussam here from Northeastern University. He's a PhD student. And he's got a very new demo of some of the research that they're doing at Northeastern. So Hussam, why don't you tell us about it?
Yeah, so our demo right now consists of a real-time communication system with the goal of accessing ultra broadband that the terahertz offers in a real-time fashion using Keysight's hardware. So over the last few years, or the last 5 years, a lot of people have been working on terahertz technology and communications, but they have one or the other, whether they have an offline system at a big bandwidth or a real-time system at a low bandwidth. So one of our competitors at the moment is NI that sells real-time communication systems for sub-terahertz, but they only give you access to 2 gigahertz of bandwidth, which doesn't make sense for terahertz because terahertz gives us the option to go above 10 gigahertz of bandwidth. So to be able to start demonstrating and playing around with terahertz communications above the physical layer and tapping into the MAC and network layers, we need a real-time communication system. So we started off with a different hardware a few years back, developing the physical layer in real time. And we were able to achieve around 8 gigahertz of bandwidth using HTG RF SOCs, radio frequency system on chips. And we were able to show it actually at 6G Symposium last year. And from there, we got the connection with Keysight in terms of how about we take our software and scale it up a little bit to match their hardware capability. Now, Keysight's hardware is much faster than what we had in terms of sampling rates. At the moment, they can go up to 68 gigasamples per second for the DACs, and as well 68 for the ADC, while our boards are only capable of 4 gigasamples per second. So that's much, much faster. So in order to tap into that sampling rate, we have to scale up our physical layer and change a few things. And at the moment, we were able to achieve around 16.4 gigahertz of bandwidth in real time. The theoretical maximum data rates that this can achieve at the moment in real time is around 100 gigabits per second, which is considerably one of the fastest real-time software-defined radios that ever exists. So what we're doing, or what we're showing right now, is a transmitter. This is the transmitter side, and this is the receiver. So the transmitter here has the baseband implemented, full software, all the packages needed implemented, and it modulates the signal, interpolates it, and we channelize each baseband channel. So at the moment we have 4 channels, each channel being 4 gigahertz wide, 4.096 gigahertz wide to be exact, and we have them multiplied by 4, so you have 16.4 aggregated bandwidth. So what we do here is basically, I don't know if it shows, but we have 4 channels, and each channel is modulated by a specific IF frequency. So we generate the sinusoid in digital, and we pick the frequency specifically to that channel. So the first channel is centered at 4.096 gigahertz, and we multiply your baseband in phase and quadrature by those sinusoidal tones to modulate that signal unconverted. And once we have all 4 channels, what we do is basically multiplex them in the digital domain, and after that it goes through the data converter, the DAC, and over the DAC cable. And now it's in the analog domain, so we can actually connect it to the VDI front ends that takes that signal in analog domain and then up converts it to the 130 gigahertz band. So that's where we have access to that 16 gigahertz bandwidth. Otherwise, we won't be able to illegally use it because the terahertz region is the only region that gives us that much bandwidth to use. So we have their VDI front end transmitter, and transmits it using this 32 dBi antenna. Similarly, at the receiver, you have the antenna, it gets the signal, down converts it to the IF band, and at the moment the receiver still needs some polishing, so we, instead of showing a receiver, we connect it directly to the DSO, where you can take a look at the signal, although it needs a little bit of aligning, but you can see the 4 channels over here, channel 1, 2, 3, and 4, although last 2 is a bit weak. So what we use in our lab is we connect an amplifier to the IF before feeding it to the front end, but that amplifier is a bit chunky to bring with us, so we decided to keep it in the lab. But if you take a look here, with using the amplifier, you can clearly see all 4 channels, how they are spaced out in the frequency domain. You see how clean the IQ constellations are. You have 4 IQ constellations for each channel that we were able to decode. And with this modulation, QPSK in particular, we're getting around 32 gigabits per second, but there's nothing stopping us from going to 60 and 64 QAM with this new hardware that we have.
And what is the carrier frequency that you're using here?
So for the RF carrier frequency, we're using 130 gigahertz. For the IF, it's channel dependent. The first channel is centered at around 4, the second is at 8, the third is at 12 gigahertz, and the final channel is at 16 gigahertz.
16. Okay. All right. And you said you were going to be showing this demo again in 2 weeks
So
at
hope-
NYU?
Sure, yeah. So the goal for NYU is to have the receiver completely ready, but as well stop using QPSK because we can obviously go to higher modulation schemes. So the goal is to hopefully jump up to 16 QAM or 64 QAM. And if somehow we get to accomplish all that in less than a week, we also are kind of interested in implementing some sort of video transmission or something beyond random data, be able to actually push some real data, meaningful data, and see it at the receiver, whether it's a video call or a file transfer, whatever it is beyond the random data being generated.